So, good morning, one and all. In the last class, we have seen what is QPSK and what is the QAM. As I told you, QPSK is a phase shift keying when we transmit 4 symbols or 4 message signals. Now, as I told you already, it is a combination of 2 BPSKs working parallelly. So, these are waveforms, and this is the transmitter, this is a receiver. So in the transmitter, what is happening here? So you have 2 independent BPSK transmitters working in parallel. In the receiver also, you have 2 BPSK receivers working in parallel. Okay, so it is just combination of 2 BPSKs working parallelly or independently. Okay, we have so here in the receiver we have a parallel to serial converter. In the transmitter we have a reverse of that, that is serial to parallel converter. So this is about QPSK. So this error probability calculations. Now this is ML rule. So we decide which symbol is transmitted just by looking at the constellation of the QPSK. So I told you in the last class the constellation of QPSK, and this is the the probability of error of QPSK. So this is an approximated expression. Here you can clearly observe that what is the probability of error of BPSK? It is Q of root 2 EV by N naught. But here it is 2 times. Here, so the probability of error of QPSK is 2 times the probability of error of BPSK. Okay, so it is approximation. So this is about the probability of error of QPSK. Now, so it is another modulation. It is called hybrid type or mixing modulation, where there is a shifting in the amplitude and as well as phase of the carrier. Okay. So this is the these are the various constellations of QAM. It is 16 QAM. It is 64 QAM. Okay. Now, so if you click on this link, you will get the 16 QAM constellation by showing amplitude variations and the phase variations for different message points. Okay, you just click it. Now, so today we will discuss the last topic of this 4th chapter. So that is a matched filter receiver. Now till now we have seen the coherent receivers. These are all coherent receivers. Why they are called coherent receivers? Because here also we are multiplying with the basis functions. So the basis functions that we use at the transmitter side are exactly same as the basis functions that we use at the receiver side. So they are in coherence. So that's why they are called coherent receivers. Now we'll see non-coherent receiver. So that is called a matched filter receiver. Now let us see what do you mean by this matched filter. It is very, very important. Now this is simply a typical receiver. Okay, now here what we do here is, so we are transmitting some signal G of t. Let us assume that it is a pulse. So that is corrupted by a noise W of t, and that is X of t is from this diagram. What is X of t? That is G of t plus W of t. Correct? Now it is given to the filter, a linear time invariant filter with impulse response H of t. It is LTI system. This is a LTI system with impulse response H of t. Now to this system or to this filter, input is X of t. Okay. Now, so output is Y of t. But Y of t sampled at t equal to capital T. Now Y of t becomes Y of capital T. After sampling, so Y of t, small t, will become Y of capital T. What we do means we replace small t with capital T. Okay. Now, so here this is very, very important. So the matched filter, this is called matched filter. It is an optimum filter which maximize SNR. Okay. So here, so our job is to choose this impulse response such that at the output of this filter or this system we get maximum SNR. What is the purpose? We have to choose this impulse response of the filter such that It maximizes the SNR at the output of the system. You know what is SNR mean? It means a ratio of signal power to noise power. So we have to choose this impulse response in such a way that it maximizes the SNR. Okay. Now in that sense it is called a matched filter. Okay. So if we can able to make SNR maximum by choosing the optimum impulse response of the filter H of t, then this is called a matched filter. Okay, we'll see one by one. So but please remember the basic idea of choosing this matched filter is to maximize the SNR at the output of the receiver. Now let us go into the details. So X of t is G of t plus W of t from 0 to capital T. Now this is from this diagram. X of t is G of t plus W of t. Now G of t is a signal part, W of t is a noise part. It is a known signal, W of t is an unknown signal. Okay. Now W of t is a noise process with a mean 0 and PSD N0 by 2. So these things already we know. So yeah, these all things I've explained just now. Now let us go to some of the mathematical parts of this filter. Now output is Yx of t convolution H of t, isn't it? What is Y of t? Y of t is X of t convolution H of t, isn't it? So output of the filter is convolution of input and the impulse response of the filter. But what is X of t? That is G of t plus W of t, convolution H of t. So G of t convolution H of t plus W of t convolution H of t. Now here we have two parts. This is the signal part. This is a noise part. Correct? Now I am writing G naught of t. What is G naught of t? That is G of t convolution H of t, and N of t, that is noise part, that is W of t convolution H of t. Now here, so here as I told you already just now, so here at the output of the filter we have signal part and the noise part. Our aim is to maximize the what? Signal power to the noise power ratio. Now, so after filter we have a sampler. It is sampling the output of the filter at t equal to capital T. We get Y of t. Now let me replace t with capital T. Now here what happens here is, now this is eta, that is SNR. So that is signal power by noise power. Now what is signal part? G naught of t. But after sampling it becomes G naught of capital T. Okay. Now what is power? Generally we take mod of G naught of t whole square. G naught of capital T whole square. Now this numerator in this expression is representing the signal power. But what about noise power? So noise component is N of t. So since it is a random in nature, we take expectation of N of t whole square. So I hope you are okay with these expressions. Okay. Now this is the SNR. It is a ratio of signal power to the noise power. So the signal power, this is signal components, and its power is mod of G naught of capital T whole square, and N of t is a noise component whose power is expectation of N of t whole square. Okay. Now anyway, so let us get into the details. G of f is a Fourier transform of known signal G of t, and H of f is the denotes the frequency response of the filter. So G of f, H of f are the Fourier transform of G of t, H of t respectively. Now what is G naught of t actually? Actually G naught of t is convolution of G of t and H of t. But what is G naught of f would be? G of f into H of f. It is simply convolution theorem. G naught of t equal to G of t convolution H of t, but G naught of f equal to G of f into H of f. I hope you okay with this. Okay. So but g naught of t is given by inverse Fourier transform. G naught of t equal to h of f into g of f. I want reverse. Okay, now what is this? So you take inverse Fourier transform, that is integration minus to plus infinity h of f g of f e power j 2 pi f t df. But so this is g naught of t. Okay, so please try to understand things in the step by step manner. Okay, so I shared the PPT, you just go through this step by step. Okay, you will understand very clearly. Nothing is there. Okay, now I have written just inverse Fourier transform. Okay, but so we want to know what is mod of g naught of capital T. Why? Because so mod of g naught of capital T whole square represent the signal power. Okay, so mod of whole square, what is g naught of t? This part, but a t equal to capital T. Wherever there is t, I am writing capital T. So here I am replacing small t with capital T here. So this is representing the signal power at the output of the filter after sampling. So just observe this carefully. Okay, but so we need to find out the noise power. You know already how to find noise power. You know PSD. So the output PSD is input PSD into mod h of f whole square. It's a filter. So something like that. We have a filter with impulse response h of t or the frequency response h of f. Input PSD is n0 by 2. What is output PSD? Correct? That is n0 by 2 into mod h of f whole square. You know all these things. How to find the noise power? It is area under that output PSD. This is what we have. So simply, so in this expression, I know numerator and the denominator. That is nothing but expectation of n of t whole square. That is represent the power. But what is the power? Nothing but area under the output PSD. Okay. Now this is what we have finally. This is what the output SNR at the receiver. So mod whole square integration z minus to plus infinity h of f g of f e power j 2 pi f capital T df by integration minus to plus infinity n0 by 2 a mod h of f whole square df. Okay, so we cannot solve this directly. So for that we have something called charge inequality. Okay, so try to understand this very clearly. Okay, what it says here is, this is very important. So integration minus to plus infinity mod x of omega whole square d omega is less than infinity, which means it is finite. In the same way, y of omega also finite. But mod integration minus to plus infinity x of omega y of omega d omega whole square is less than equal to individual integrations. Integration minus to plus infinity x of omega mod x of omega whole square d omega into integration minus to plus infinity mod y of omega whole square d omega. This is inequality. You observe very carefully. But when it is equal, so here this quantity is less than equal to these two quantities, the product of these two quantities. But when the equality holds good, the equality holds if and only if x of omega equal to y of omega or x of omega equal to some constant k into y conjugation of omega. So if the real quantities, the equality holds good when and only x of omega equal to some k into y of omega. Otherwise it is less than when they are equal. When they are equal, if and only if x of omega equal to k times y conjugation of omega. Now, so something like that. We have this, we have right hand side, we have quantity that is less than equal to these two quantities, product of these two quantities, but these two will be equal if and only if x of omega equal to some k times, k is a constant, y conjugation of omega. Okay. Now we will apply this inequality where? In the numerator of this expression. Here also we have two product of two quantities. What are they? H of f into g of f into e power j 2 pi ft. Okay, I will call this as one quantity and this is another quantity. Something like this is x of f, this is y of f. Okay, now I will apply this inequality to the numerator part of the above expression. What will happen? Now to this expression I am invoking the charge inequality. Then what will happen? So that is less than equal to this quantity first. Mod h of f whole square df integration this quantity. What is the quantity now? Mod g of f into e power j 2 pi ft whole square. Anyway, so e power j 2 pi ft mod of that will be 1. So this is what you have finally. Okay. Now the numerator of the above expression is less than equal to the product of these two expressions or quantities. Then finally what would happen? This is what you get. Now this eta will be, so you can clearly write here otherwise. What you can write here? So this is less than equal to, what you can write? So what is this quantity? Just now you told me. What is that? Integration. What is numerator will becomes? Minus 2 plus infinity h of f whole square into integration minus 2 plus infinity g of f whole square. This is g of mod g of f whole square. This is h of f. That is h of f. You try to write it properly. This is h of f whole square. Mod is there by what you have in the denominator? N naught by 2 is anyway constant, take it outside. N naught by 2. So integration minus 2 plus infinity mod h of f whole square. Then what happens? So these two are cancels out. Now this will be less than equal to integration minus 2 plus infinity mod g of f whole square by n naught by 2. That is what you written. So n naught by 2 becomes 2 by n naught. Now this output SNR is less than equal to 2 by n naught integration minus 2 plus infinity mod g of f whole square df. But so when this is maximum, what is the maximum value of this? The maximum SNR is equality, right? Suppose if I say x is less than equal to 2, what is the maximum value of 2? Suppose 3. So what is the maximum value of x? 3. In the same way, so what is the maximum value of this SNR? That is equality, which means 2 by n naught integration minus 2 plus infinity mod g of f whole square df. So this is a maximum SNR. But when it is maximum, go to inequality. Correct? Which means x of omega should be equal to some constant k into y conjugation of omega here. Which means what should happen? H of f should be equal to some k into conjugation of this quantity. Correct? Yes. So h of f optimum, h of f equal to k into conjugation of the next quantity, that is k into g conjugation of f. What is the conjugation of e power j 2 pi ft? It is e power minus j 2 pi ft. This is the optimum frequency response of the filter. Because see, so please understand the logic. So if it is so, you get the maximum SNR. How much is that? 2 by n naught integration minus 2 plus infinity mod g of f whole square df. So in order to get maximum SNR, the frequency response of the filter must be equal to some k into g conjugation of f into e power minus j 2 pi f capital T. But you take the inverse Fourier transform. This is h of f. What is h of t? This is h of t. K into g conjugation of capital T minus small t. So you try to get the logic here. It is a concept of inverse Fourier transform from the signals and systems. I am not explaining all the things here. You just try to get the logic. Okay. Now generally we take k equal to 1. Okay. and here so optimum equal to, so if I remove k anyway you can write k also, so g of capital T, here I am not writing conjugation also because I assume that g of t is a real signal, but this is a generalized expression for the impulse response of the filter, an optimum filter. Okay, what is that? K into g conjugation of capital T minus small t. But here I am not writing conjugation because I assumed that the signal is real. Okay, if it is not real, you must write the conjugation. Now k also you can take 1. Okay, now anyway, so g of capital T minus small t, which means k equal to g of minus of, this is very important, minus of small t minus capital T. You understand this? Here we are talking about some elementary operations on the signals. Okay, so something like this. So if you are given x of t, I gave you x of t, I am asking you to find out what is x of capital T minus small t. How to find out this? It is the basic operations of the signal. Basic operation means time shifting, time reversal, something like that. Okay, here so what is the known signal? X of t. From that you have to find out x of capital T minus small t. In the same way, what is known signal? G of t. From that you have to find out what is g of capital T minus small t. How we find out? We need to do two operations, or what are they? Time reversal, next time shifting, or shifting towards right side by capital T. So please understand this logic very carefully. So to find out the impulse response of the filter, we need to do two operations, that is time reversal followed by time shifting towards right side by capital T. Otherwise you just think about the logic of finding the x of capital T minus small t given that x of t. Okay, now this is the impulse response of the matched filter. Okay, now they gave you s of t or g of t or s of t. They gave you like this. They are asking the impulse response of the filter that is matched to the signal s of t. What is that? H of t equal to s of capital T minus small t. Now what will happen? How to find out that? How to find out this quantity? S of t is given to you. They are asking s of capital T minus small t. Here capital T is any arbitrary value. It is a constant. Okay. Now what will happen? Can you guess? First of all, what do we do? So if you are okay with the concepts of S and S, you can write directly. Otherwise, you do two operations. First of all, you do time reversal. First is do time reversal. That's the first step. Second step is after time reversal, you take a time shifting towards right side by T. Let me write here. First of all, let me take this. First of all, do time shifting. What will happen? Time shifting means what will happen? Time reversal. What will happen? You take time reversal of this. The time reversal. This is minus t. This is 0. You just s of t, this is s of minus t. Correct? It's over. Next, after this, you try to get the time shifting of the signal towards right side by t. Then what will happen? This is what the impulse response here. So in the questions, they will give you the signal. They will ask you to find out the impulse response of the matched filter. So that simply depends upon signal s of capital T minus small t. Here I have written G. No problem. G or S. It is just representation. So you try to remember these things, very important. Okay. So these things are very important. Yeah, is the time reversed and delayed version of the input signal. Okay, so what is the impulse response of the filter? That is the time reversed and delayed version of the input signal. Okay, G of t. Now So here, what is the energy of g of t? Integration minus to plus infinity g of t whole square dt, that is also equal to integration minus to plus infinity mod g of f whole square df. How can I write like this? What is that rule? Parseval's relation. Okay, I hope you are okay with this relation. Now, but what is the output SNR? The maximum output SNR, that is 2 by n naught integration minus to plus infinity mod g of f whole square. But what is this? Is nothing but energy of the signal. Now that is 2e by n naught. So this is the maximum SNR that is possible at the output of the filter after sampling. 2e by n naught. What is E? E is the energy of the signal. Okay. So when the output is maximum, when the output SNR is maximum, when the impulse response of the filter is h of t equal to s of capital T minus small t, or when the impulse response is time reversed and delayed version of the input signal, then we get maximum SNR. But what is that maximum SNR? 2e by n naught. What is E? E is energy of the signal g of t. Okay. Now, so let us go to the some specifications related to the matched filter. So matched filter for a rectangular pulse. Here I am assuming g of t is a rectangular pulse from 0 to capital T. Okay. T is an arbitrary value, so it is not time period generally. It need not be time period, just an arbitrary value actually. Now, this is g of t. What is this h of t? Can you find out? How to find h of t? First of all, what do? We take a time reversal. So it is 0 to t becomes 0 to minus t to 0. Next, that is the first step. Next we take delayed version, delay by t seconds. Then what will happen? Again 0 to capital T. Same. Now in this scenario, what is happening? So g of t is same as h of t. We got same. So this is h of t, this is g of t. This is a known signal, this is a impulse response. Okay. Now, so what is g naught of t? The output of the filter, that is g of t convolution h of t. So it is convolution of two rectangular pulses. What is that? That is a triangle. You know already. You try to do convolution of these two. So you get something like this. This is a rectangular pulse, that is output of the filter. Okay, I hope you are okay with this. So in this scenario, what happened is g of t is same as h of t. So which means output of the filter is the convolution of two rectangular pulses of same width. Then you get a triangle. From where to where? 0 to 2t. Now it is maximum at t equal to capital T. So what is this value at t equal to capital T? That is say k, anyway constant, a square t. Okay. So now you tell me. Now the reason is, now you can ask me why you are sampling at t equal to capital T. I am sampling at t equal to capital T because at this value the signal component is maximum. So what is g naught of t? The signal component of the output of the filter. Now if I take the sampling at t equal to capital T, I am getting the maximum value of the signal or maximum signal power. Okay, that's why we are generally sample at t equal to capital T. Okay. Now, so if sample at t equal to capital T, so that is k into a square into t. Anyway, k is a constant. You can take k equal to 1 also. What is that value? A square into t. But what is a square into t? Energy of g of t. What is energy of the signal? How to find out generally? 0 to capital T, g of t whole square dt. What is g of t whole square? A square. A square dt. What is this value? A square into t. Now, So if you sample at t equal to capital T, you are getting the maximum value for the signal component, that is nothing but its energy, that is a square into t. Okay, anyway, so that is about the matched filter, and this is one example. You try to find out the answer. There is homework for you, and this is answer. This is answer to this. Okay, so try to find out the answer for this question. So here this is a logic. Okay, so for matched filter, if the input is a rectangular pulse, the impulse response of that filter is also same rectangle. Now the output is a triangle, so which is having a maximum value t equal to capital T, that is a square t, but that is equal to energy of the signal. Okay, that is the logic. So try to find out the answer for this question. So that is about the matched filter receiver. Yeah, now this will act as a receiver. Now remember, so it is a non-coherent receiver. Why? Because nowhere we are talking about the basis functions. We are not multiplying with any kind of carrier. It is just like non-coherent. Okay, there is no question of having a carrier. Multiplication of the carrier is not happening here. Okay, now this will act as a receiver. Okay, so we don't study much about this, but anyway, just introduction to the matched filter. So this is about the non-coherent receiver of the digital modulation schemes. Okay, so with this we complete the 4th chapter also. Okay, so in the next class we start the 5th chapter. So thank you.